Hello everyone. In this video I'm going to show you another way of generating a random distribution. So in my previous video I showed you a simple trick to generate random numbers between two defined ranges, and the distribution of that random number is uniform. That means every value is equally probable. But in many of our applications, for example, if you want to assign velocities to your atoms, you have to obey Maxwell's distribution. That is a Gaussian distribution. So that is one example, and another one is if you want to do Langevin dynamics, you have to again generate a random number distribution that is Gaussian. So I want to show you how to generate or how to transform the uniform distribution of random numbers into a Gaussian with a mean value of 0 and a standard deviation of 1. And in simulations, we require this technique more than we require the uniform distribution of random numbers. So let's get started. So before getting into the technicalities, I would like to show you a paper by Box and Muller, who actually showed how you can generate a random normal distribution. And their equations are these two, where you take two independent random variables from the same rectangular density function on the interval of 0 and 1, and say the values are u1 or u2, and you can define two variables which uses this logarithmic and cosine, a combination of these two functions, to give you a random number that follows the Gaussian distribution. You can see they have written then x1 and x2 will be a pair of independent random variables from the same normal distribution with mean 0 and an unit variance. And they have given a proof, a justification. You can look up this paper. It's available as open access paper, so you don't need any credential to open it. And it's just a 2-page paper, so it's very simple way to generate random distribution, and we are going to use this formula. So let's get started. So I have already written a very small code for a Box-Muller random number. Let us first see that, and as you can see, I have two variables u1 and u2, which are the two random numbers that is picked up from an uniform distribution, and then I'm using the Box-Muller formula to define another variable x, which is a combination of u1 and u2, a function of u1 and u2, and then I'm writing it in a file named fort.3. And the code is very straightforward and simple, and this will give you a 10,000 random number which is distributed in a Gaussian. Okay, so let's run this. Okay, and you can see there is a new file called fort.3, and the fort.2 is a file that contains the output from random.f90 code. So let's see the code, and this is the part of one of my earlier videos where I showed how to generate uniform random number. So in principle, this 4.2 contains 10,000 uniformly distributed random number, and 4.3 contains 10,000 Gaussian distributed random numbers. So let's check how the distributions look like. So I'm going to use XMGRIS, but you can use any plotting software of your choice. Let's open 4.2 and 4.3 together. Okay, and so the black one is 4.2 and the red one is 4.3. So let's make a distribution out of it. Going to data, transformation, histograms, and let's select both of them together, normalize, and the range is -10 to +10, and number of bins could be 100. Okay, so now I have to hide these two and click on auto scale, and you can see the blue one is the distribution out of the red fluctuation graph. So that gives you a Gaussian distributed random number with mean value at 0, and if you calculate the standard deviation, it will be 1. On the other hand, the green one, which is the distribution of the black fluctuation graph, it's uniform. That means all the values are equally probable. So this is a way to generate Gaussian random numbers, and thanks for watching the video.